Roberts, and he'll speak about magnetic defects and neuron defects.
All right, thanks. I want to thank, of course, like everyone else, thank the organizers and the Institute for hosting us. This has been a very useful conference for me. I'm a physicist and I have been here for a good week being forced to learn math, which is something that I should do, even though I don't. But I'm going to talk about physics, or at least as much physics as any string theorist can do. I'm going to talk about magnetic defects and RG monotones. This is some work that I did with my now longtime collaborators Igal in Leuven, Jerome Gauntlet and his current student Yusheng at Imperial, and Chris Rosen in Crete. It's based on these two papers, and I mostly put this here to point out that this first paper is 94 pages and the second one is 72 pages. So I'm going to be telling you results, and I'm going to maybe try to tell you a story of how we did some of those calculations. But because we were figuring a lot of these things out as we were going, if we were to rewrite these papers, we could probably make them shorter, but there's fiddly bits that I'm not going to tell you the details of, but they're all in these things, but as you see, they are long things to go through. Also, because these are so dense, I'm certainly not going to tell you everything that's in them. I'm going to pick out, what I think is the most interesting parts of them. Let's start. And again, as always, please stop and interrupt me with questions, because if I lose you and you have no idea what I'm talking about, then this is kind of a waste of all of our time. Right, so what am I going to talk about? I'm going to talk about, well, the word that I hid in the title, supersymmetric magnetic defects. So I'll start with a review, but it's been reviewed by basically everyone about defects, RG flows, and defect CFTs. And then we will focus for the entirety of the talk on magnetic defects. Lots of different things can be called magnetic defects. I will tell you specifically what I will mean when I say magnetic defects. It's not the only thing that could be a magnetic defect, but I will tell you exactly what I mean in this context. We'll talk about the dynamics of the defects, RG flows between different defects theories, and we're going to make a guess for a particular new type of RG monotone. So let's begin. Okay, I have a motivational slide but okay, I don't think I need to motivate the audience at this conference that we are interested in defects. But the main question that I personally am interested, at least in this project, is how do RG flows behave in theories with defects? What are the new types of fixed points? Is it always what we would call a defect CFT? Can you have things that are more general? And is there a generalization of the C theorem and the F theorem and the A theorems to mixed dimensional theories? There are partial answers to this, but of course there's no systematic understanding because it's just a much bigger zoo. But this is the goal, is to at least come up with a guess. Yeah.
So you mean that most of the balance is slow?
Yes, indeed. Right. I have a system that is mixed dimensional, which means that there's maybe a defect which maybe has degraded freedom or not, and I'm just want to take that and turn on anything that is relevant and float to whatever else I can get. But indeed, this is what I mean when I say there are, of course, partial results, but not full results. So we've seen this before, but let's just remind ourselves of the conventions that I will use. If I have if I have a d-dimensional field theory, and it's Lorentz invariant and local and unitary, and I can't spell unitary right, we expect that if you flow to the deep infrared, you should get a CFT. That CFT has the conformal group as its symmetry group. If you add a defect on some p-dimensional subspace, and then I flow again, so I maybe add boundary conditions or new degrees of freedom, a new term in the Hamiltonian that's localized on that subspace, whatever you like, you can ask again, I flow to the infrared, I flow below all scales that I've introduced, what am I left with? Just by counting symmetries, the things that could be preserved as a subgroup of the conformal group, well, at the level of the algebra, right, I will preserve parallel boosts and rotations and special conformal transformations along the defect. I will preserve dilations, which act both parallel and transverse to the defect, and I can preserve transverse rotations. And so we generically write this as SOD2 breaking to SOP2 cross SOD minus P, right? There's lots of assumptions, but I'm going to assume that my system will end up at a fixed point with these symmetries. I just want to point out that it's an explicit assumption, right? Because as I build my theory, I've included scales, and I'm just going to assume that the endpoint is a system with scaling symmetry that acts homogeneously. Things scale the same way along the defect as they scale transversely. If my whole theory started with something that's Lorentz invariant and local, I don't actually know any counterexamples, but I don't know of a proof that that's what has to happen. All right? But we're just going to assume that. Otherwise, you'd have different structures of the dilation group, and it wouldn't be this clean subgroup. Now, even though you have a lower dimensional conformal group, as many people have said here at this conference, what you don't have is a lower dimensional CFT. One of the ways you can see that is because I don't have a lower dimensional conserved stress tensor, right? The divergence of the stress tensor is non-zero on the defect, and it gives you the displacement operator, which at a Hamiltonian level is literally, you've done something to your Hamiltonian that puts a defect in, and I change the Hamiltonian by moving where the defect is. It's any time you have a defect, you naturally have a notion of a displacement operator if the theory was originally local enough. All right? Now, because of the reduced symmetry, one-point functions in the presence of a defect can be non-zero. In particular, the stress tensor can have some non-trivial power law dependence moving away from the defect where I've suppressed all of the index structure here. The important thing is that there's a number sitting in front of this HD, which is sometimes called the defect dimension. And if I have any operators, primaries, for instance, will have fixed power laws as well, currents, etc., right? And of course, this is then a mixed system. I have bulk degrees of freedom, so bulk operators, and I have defect degrees of freedom, and therefore defect operators. Again, this is all a review. We've seen this because we've been here for a while. So now I'll tell you what I am going to talk about when I talk about magnetic defects. And as a physicist, it's the easiest thing that I can think of. It is a magnetic solenoid, right? You take a current, I run it in a wire, I coil the wire, and when I run the current through, what do you learn in high school? You learn you generate a magnetic field. The magnetic field is big on the inside and it's small on the outside. Maybe you don't go this far in high school. If this coil is infinitely long, then there's a constant magnetic field inside of the coil and the magnetic field is zero outside of the coil. You can then push this further. I can say not only is it infinitely long, but it's also infinitely thin. So I squeeze all of the magnetic field into a delta function, right? In that limit, where here my coordinates are now z, let's say, is the direction along the defect. I have x and y, and I'm always going to be in 3+1 dimensions. F is a delta function on the defect times some number. Now, by dimensional analysis, mu is a number, because F is a field strength, and all of the units are taken up with dx and dy, right? And the delta function. You can take this field strength and integrate it trivially into A. So I say A is mu d theta, where theta is now just a nice axial coordinate. And this is fine because theta is a bad coordinate at the origin, and so A is not actually closed. When you take it, you see F as this delta function. And you use Gauss's law, and you easily measure this, and you say, indeed, the flux through this solenoid is just mu. In fundamental units, I've said h bar and e to 1. All right? Now, what else do we remember about quantum mechanics and magnetic fields? We hopefully remember that if I have a magnetic field and I take a heavy charged particle and I adiabatically wind it around the magnetic field, I shift by a phase. And in this very simple example, that phase is really simple. It's just e to the 2 pi I mu. That means that if I've picked units where all of my degrees of freedom have integer charge once I've set e to 1, that means that mu isn't really a number. Mu is a number that lives on a circle. Because if I take this phase and I shift it if I shift this phase by shifting mu to 1, g doesn't change, right? And that's just the statement that if I have a true integer amount of flux in space and I wind charged particles around it, I never see it, right? That's the magic of the Eremov-Bohm phase. So this magnetic solenoid is what I am going to mean when I say magnetic defects. Is this picture clear? Just infinitely thin, infinitely long magnetic solenoid in this example in 3+1 dimensions. We're happy? Good. Now, let me try to make a connection to some of the other things that we've talked about in this talk. Yeah. Yes. Yeah. I'll touch on this a little bit closer. Yes. So I'm talking about this in the language of a magnetic field, but I'm not really thinking of this as a dynamical gauge theory. This is going to be an external source that I've turned on. Yeah.
Usually people call this twist defects. I think
Yeah, that's what I'm going to talk about right here. Right? So, indeed, look, I have A, and A is mu d theta. Can't I just gauge this away? Well, you could gauge it away, but theta is not really a good coordinate. And so what ends up happening is that it's a singular gauge transformation. But what you'd end up doing is you introduce, indeed, exactly this, twisted boundary conditions, right? What that means is that as I look at my plane, I have some surface extending out in one direction and terminating on the axis. And as I wind around the axis, I necessarily have to go through this surface once. And this surface is supporting some topological symmetry operator, right? Because the boundary condition is just whatever my field is. Psi of theta plus 2 pi is some phase shift times psi of theta. So indeed, all I've done is I've put in some topological symmetry operator. This is the simplest thing. It is a abelian regular zero form symmetry surface operator, but it has a boundary, right? And even though over here the operator is topological, once I give it a boundary, the boundary is no longer a topological object, right? That's a fixed, very special point. Right? So you can think of this indeed as, right, I have some unitary that's Q integrated over the surface, but that surface has some boundary sigma, which is exactly where I'm saying my defect is. And the important thing to take away from this is that even though it looks like I've defined this whole system with mu as a pure number or f, and f really lives only on the defect, mu is not a defect marginal coupling, right? Because the only way that I can write it down covariantly involves writing down things that live in all of space, right? It's another way of saying this is I cannot think of this as turning on the defect by adding a term with a good gauge invariant operator localized on the defect. So it is a good codimension 2 defect in 4 dimensions, governed by some number mu that really lives on a circle. But mu is not a defect marginal coupling, right? It's something else. I don't know if the right language is to call it a bulk marginal coupling, because it's certainly not a homogeneous marginal coupling, but it is something that I have to build out of the whole bulk theory. Let's finish the line of reasoning as we connect to previous things that we've said about defect CFTs. We said that when I have a defect CFT, the divergence of the stress tensor is non-zero. Well, that's fine, because I have a system with a global symmetry, and I've turned on an external background field. So I know that I have a ward identity. The divergence of T is just J dot F, right? It's just the force law. F is some delta function supported on the defect. And so you immediately identify what the displacement operator is. It's the current operator that exists everywhere pushed onto the defect with some overall numerical factor. In fact, it's curled, so the displacement in the x direction is related to the current in the y direction, and vice versa with the sign flip. Right? So we can play the game of identifying different pieces of this as being a standard 4D, 2D defect CFT.
this extreme is actually not the curve.
Yes, there's an epsilon ij here. So if because of the magnetic field, I displace in the x direction, the operator that is the current in the y direction. If I displace in the y direction, I get the current in minus the x direction. Yeah. Only, of course, on the defect. This operator only lives on the defect.
Can't you think of this equation as being the reflection of the rotations from the defect are broken? If you take rotations in the global symmetry, that's the stuff.
Yeah, exactly. There's a diagonal between the U1 and SO2. Yeah. This was asked earlier, but I just want to re-emphasize this. Even though I use the word magnetic field, one should be careful. This is not a dynamical gauge field. A is a background field for a global symmetry, the usual guy that we love to introduce in quantum field theory so that we can get a generating functional out of which we can extract current correlation functions. But since this was already asked, I'm not going to spend too much time on it. So I've told you the physical system that I have, a magnetic solenoid. Before we sit down and do calculations, As physicists, we love to guess what the answer will be before we do the calculation and see if we're right. So what do you expect, right? If I have a charged particle moving in the background of this solenoid, well, if it doesn't hit the solenoid, nothing happens. There'll be some phase shift if you do some careful measurements of going through one side or the other, but locally, there'll be no effect. But if a charged particle hits the solenoid, and I imagine that it's not really a delta function, I fatten it up into something of finite width, the particle will enter the solenoid, it'll start to turn in a cyclotron orbit, and then it'll exit the solenoid. All that means is that particles will get deflected as they scatter through this. That's a scattering statement. I can then think about what happens if I do a pair creation problem. If I pair create two particles near the solenoid, and then one goes into the solenoid and one doesn't, the one that goes in will get deflected, and it'll generate some current. And so you would expect to generate some non-trivial current flow around the solenoid. It's a magnetic field, so it can't do any work. But that's fine. You could have currents circulating without having done work to a system. It's also, this is related to the fact that, of course, we've turned on a magnetic field. Magnetic fields break time reversal, so there's no problem with having some current circulation. And as has been pointed out by other people previously, indeed, the general structure of one-point functions will essentially be fixed by all of the residual conformal symmetry up to a bunch of numbers, but those numbers will depend on our amount of magnetic flux, or equivalently the monodromy parameter. So let's just write down what these things are. So, as we said, you can have circulating currents, so the current can only be pointing in the theta direction. By dimensional analysis, it has to look like 1 over rho squared. That might seem funny because you'd say this is a current operator in 3 dimensions, but theta is a dimensionless coordinate. So this is the correct dimensionless statement. With some number sitting on top, c of mu, this is so far some unknown function, right? Mu was the amount of flux, and c, we don't know what it is. All we know is that as mu goes to 0, c had better vanish because then there's no defect whatsoever. Other than that, a priori we don't know what will happen. You do a similar calculation for the stress tensor. You see, here we write down the whole Gori index structure. What really matters is that, indeed, the stress tensor is traceless, but the components are non-trivial, and there's, again, some function HD that we don't know, right? To understand the local dynamics, just the local dynamics of the defect, basically boils down to measuring this function C and this function HD. Then you know what the pressures and the shears of the system are and what the current flows are. Yeah?
Is this any bulk theory with U1, or is this a specific bulk theory with U1?
I've made no assumptions. I just have a U1 global symmetry that I've turned on this thing for. That's all I've done. Yeah. And in fact, this statement about the stress tensor is even more general. That's just codimension 2 and 4 dimensions. Now, we take the leap from the thing that you can build into the laboratory to the world of formal theoretical physics by pointing out the following thing. The symmetry breaking pattern of going from the 4-dimensional conformal group to the 2-dimensional conformal group with transverse rotations, flat space with a line defect is not the most general system that preserves that. You could, if you were so perverse, imagine instead saying, no, when I take a cross section transverse to the defect, I also allow there to be a conical defect as well, right? I take this slice and I say, no, I actually maybe cut out a wedge so that there's a conical deficit, or I stick in another wedge so that there's a conical excess, right? You could do that at the level of a metric or a line element by just saying, I have what was almost standard cylindrical coordinates, except I just rescale the angular coordinate by some factor n, but I'm telling you that this angle theta is always periodic 2 pi. Now, if this angle is periodic 2 pi, and n is not 1, there's a conical singularity. You could do the calculation. It's easy. You see, indeed, the curvature looks like n minus 1 times a delta function sitting on the defect. This is maybe a formal exercise so far, but in some level, this really isn't that different than the magnetic solenoid defect, right? The magnetic solenoid defect was F. Where did we write it down? It was F is a delta function on the defect. And so why not let another curvature be non-trivial on the defect? Why not let the Riemannian curvature be non-zero on the defect, right? Of course, this you cannot build in the laboratory, but you could do calculations in this system just as easily, right? Now, this just seems like a nice thought experiment, but because of supersymmetry, we'll discover we need to do it. Yes?
I'll note that I think this can be built in the laboratory if you consider a crystal with a disclination. If you cut out a wedge of the crystal and glue it back together. For like graphene, these conical singularities arise.
Sorry, yeah, you can build conical singularities, but I don't think I could really stack them into a 3+1 dimensional system.
Yeah.
In 2+1 dimensions, yes, for sure it would be different. In 3+1 dimensions, I don't think this works. Certainly you wouldn't get some nice Lorentz invariant low energy theory, but it's a good point, yeah. Let's say it's difficult. Okay, but because we had supersymmetry in the title, we are going to discover that indeed, sometimes it's not a choice to put that conical deficit in there. So let's do the blitzkrieg lightning review of supersymmetry. If I'm studying systems with supersymmetry, all that means is that the system doesn't just have isometries or killing vectors of the space in which you're working. It has fermionic symmetries as well. Fermionic symmetries are killing spinors instead of killing vectors. And the killing vector for the system that we're looking at is something like this. It's roughly the covariant derivative of the spinor needs to be 0. It's a spinor, so it couples to the spin connection of your manifold, so you're already immediately working with a manifold with spin, and it's charged under a particular U1 global symmetry, so there's some standard coupling to a background gauge field. Solving this in general is an interesting but difficult problem, but you can jump to the answer by, for instance, looking at the commutator of these. If it's a killing spinor, the commutator has to be 0, but this is great because the commutator of derivatives is curvatures. There's two types of curvatures that show up. There's the Riemannian curvature, and there's whatever the U1 field strength is here, all right? And so if f is a delta function in this equation, I can easily satisfy this by saying r is a delta function in this equation, except for the small problem that there's this gamma matrix in there. That's easy. You say I'm going to impose some projection condition that throws away half of the supersymmetry. This is what's sometimes called a chirality condition. And so indeed you find that, great. If f is whatever it is, I can pick r to have either a conical deficit or conical excess, pick the right sign, and I preserve supersymmetry. For those who have seen it, this is just an ultra-local conical singularity version of the topological twist, where I'm just balancing SO2 curvature against U1R curvature. That's all we've done. But you have to make a choice, right? If I fix a background, I fix what this curvature and I fix what this curvature is. So I can never preserve it for all of the supersymmetry. I'm always throwing out half of it. Right.
Sorry.
Yeah.
Would you expect that in general defects will break half as a supersymmetry, or you're trying to?
That's exactly what's happening here.
Okay.
Right? So we could do a counting argument, which would be if I was starting with the 4D(n=1) theory, and I have a system that only has 2D Lorentz invariance, so I have to do my counting with 2 dimensions. So 4D(n=1) reduces to 2D 2,2. And this is a chirality condition, so it throws away either the first 2 or the second 2, so these will generically be 0,2 defects. Generically. You can sometimes play games to get enhancements. But yeah, that's exactly right. I'm exactly expecting this defect to, at best, break half of the supersymmetry. But that was a counting argument for an n=1 theory. We'll see that even if I start with an n=4 theory, I'm left with something that's 0,2. Great. So I told you a story of what the local dynamics of a defect would be. I haven't calculated it for you. People in this audience have calculated it in other theories. But that's not all there is. In a 4D 2D system, people have in fact worked out at least the parity even sector of the trace anomaly for these mixed dimensional systems. Now, the ambient space is 4-dimensional, so you have the usual ambient space terms with the C and A anomaly coefficients sitting in front of Weyl squared and the 4-dimensional Euler density. And it turns out that for a 2-dimensional defect in 4 dimensions, there are 3 new terms localized on the defect, 3 new anomaly coefficients. There's B, something that really looks like the 2-dimensional C central charge. This B is the guy that we know satisfies some monotonicity theorems. And then you have 2 other guys, D1 and D2. For those who know what these things mean, B is type A. It does not depend on defect marginal couplings. D1 and D2 are type B, and they are allowed to depend on them. But I want to emphasize, mu, the monodromy parameter, is not a defect marginal coupling, and so B will depend on it. There's an interesting calculation to be done, right? And indeed, there is a B theorem. If I have a defect RG flow, I turn on a source for a relevant defect operator and drive an RG flow, you know that B has to decrease. But that's all that's known. That's the only theorem that we have for it. We could say a few more words. Yeah?
Does the magnetic field break parity? So shouldn't you lose parity on terms of the trace?
No, because the whole theory is parity even. So there are F wedge F type terms, but they're not activated because I only have magnetic fields.
Parity on curvature.
I think in this simple system they're not turned on.
Okay.
Because all of your curvatures are delta function dx dy. So even if you try to build some mixed term, I don't think you can get it to be non-zero. For this particular background, there are another, yeah. Now you can ask, how would you measure these guys? And you play the usual game that you play. It turns out that with some fun story of Weyl transformations, it turns out that that coefficient sitting in front of the stress tensor 1-point function, HD, is just fixed by the second of the B-type coefficients, D2. Furthermore, if I have 0, 2 supersymmetry, D1 has to be equal to D2. And there are arguments that B should be independent of some bulk marginal couplings. We'll come back to this point later, but you might think that, this could be nice because I could do the calculation for n equals 4 super Yang Mills at strong coupling or at weak coupling and see if they agree. And people in this audience did the calculation at 0 coupling, so I don't have to do it. So if I want to measure D1 and D2, I just have to look at these 1-point functions. But they're not the interesting ones, right? The A-type anomaly is the interesting one, and it's harder to calculate. But again, other people have thought about this problem carefully, and they figured out how to do it. There's a cute game where you take your flat defect, you do a conformal transformation to map this line to a circle, which then has curvature, to a sphere, which then has curvature while keeping the ambient space flat. And playing games with this, you can make an argument that the free energy in that system, its derivative with respect to mu, should give me a current, because mu is just the external gauge field, but the free energy is a derivative with respect to mu. The free energy should be related to the trace of the stress tensor, and so you can relate things like stress tensor correlation, the trace, and the trace will pick up B and D1 and D2. And on the other side, just taking derivatives with respect to mu gives me currents. You go through this calculation a little bit more carefully, and you extract exactly this identity above. We were not the people that derived this. What we did is we figured out the careful way of putting in the n of the conical deficit. All right. So if I measure all of these current at 1-point functions, I have a differential equation that I can try to solve. That's not quite enough, though. You really also need to know how the system is responding to the conical deficit. So there's one additional equation that you have to work out, but the argument is more or less the same. It's just that changing with respect to n is like changing the metric, and so it's a stress tensor 1-point function, right? And that's why you get this equation here, where D2 was the output of the stress tensor. The moral is, this is a set of differential equations. If I can calculate T and J, I can try to solve those differential equations, integrate them up, and get what B is. With the boundary condition that if I turn off all of the magnetic fluxes and I turn off the conical deficit, there's no defect anymore, so the boundary condition is there, the defect B should be 0. So that's the exercise that we want to do. We want to calculate these one-point functions and use them to measure the one missing A-type anomaly coefficient.
So
Yeah?
Ci was a theory-dependent quantity, or now you chose the theory.
I haven't yet specified a theory. I'm just assuming that there's some U1 to the n global symmetry that I can turn on fluxes for. Now, that argument that I gave for measuring B is of course not the only way to do it. You could do what in my mind is a conceptually easier but computationally much more difficult problem, which is to calculate the entanglement entropy between a ball threaded by your magnetic defect and the region outside of it. If you just work out what this generally has to be using the standard arguments of Weyl transformations and free energies, the entanglement entropy, well, of course, it has a power law divergence that's not universal, and we don't care about it. And then there is, of course, a logarithmic term that depends on the bulk A-type coefficient A that shows up with a log of cutoff. But because of the defect, there's two additional terms. There's a B minus D2 over 3 with a different factor in front of it that also shows up. So if you could do this calculation, either just in free theory or holographically, however you wanted to do it, you already know what A is. One-point functions gives you D2, and so you should be able to extract B as an independent check. I mostly just like to put this here because I want someone else to do it. I don't want to, it's all there in the literature. People have given you almost every step. It's just technical and fiddly, and one only has so much time in the day. The other thing, however, that is worth pointing out is that this is the story when there is not a conical deficit here. And please, someone correct me, to my knowledge, it is unclear how this generalizes if there's also a conical deficit. Because then it's really an almond, it's not a sphere, things are more complicated. The only other thing I want to say, indeed, is that, look, I have -4 and a B and D2. If I didn't have the defect, this coefficient would just be A, which is monotonic, and you can make the usual relationship between A-theorem monotonicity and some monotonic properties of the universal part of the entanglement entropy. That breaks down with the defect.
So this entanglement entropy with what is the entanglement surface?
A ball of some radius that I've called L, which exactly threads the defect. So the defect pierces the north and south pole. So this is now an even less symmetric situation, because putting this ball in further that completely breaks the conformal symmetry down to some rotation. Great. Okay. So I hope I've given you the framework of the particular type of defect I am interested in and the things that I would like to measure. Now, I'm not the first person to think about these types of defects. People have done all of these calculations for free theories. Free theories, however, it's a very useful result, but monotonicity in only free theories is trivial, because if I only have free theories, the only RG flows I can ever have is gapping modes, right? And that means that A and B and C, all of them, are just going to be some number times the number of fermions or the number of bosons that you have charged in your system. So if I turn on a mass for one of them and I remove it from the system, that number in front decreases and monotonicity is trivial, right? It's good to know that it does indeed decrease, but when your anomaly coefficients are literally counting free degrees of freedom, monotonicity is not that exciting of a result, right? So we would just like to have an example of what these expressions look like in a system with interactions. And of course, studying this in a system with interactions perturbatively is a nightmare, right? Even the free calculation, the Green's functions that you're working are built out of Bessel. I don't know how you guys did it. It's a beautiful paper that some of the people in this audience did where they did these free results. And it's wonderful, and I'm glad that they did it. So I didn't have to do it. So instead of doing some perturbative calculation, I'm going to do the thing that I've done more or less my entire career, which is use the toolbox of holography to do a calculation that will give us B for a strongly coupled theory with the gravity dual. Before I get into that, are there questions? No? Good. I'm going to assume everyone in the audience either understands what ADS-CFT is or can believe that it exists as a black box that lets you do calculations for supersymmetric quantum field theories at large n and large coupling, et cetera, all of the usual caveats. So what is the secret that we will use? The symmetry of the conformal defect is SO2 cross SO2. Now, when we're doing holography, or in general studying conformal field theories that don't have diff anomalies, I can change the vial frame, and up to keeping track of how the anomaly propagates through, I could do a calculation in two different vial frames, and I know exactly how to map all measurements from one vial frame to the other. And in particular, if I take my cylindrical coordinates and I divide by rho squared, the radial coordinate, this just turns into ADS3, and this just turns into a circle. That's a boring statement. That's just stating that cylindrical coordinates is conformally equivalent to ADS3 cross S1. Now, if I have a conical deficit in this frame, what have I done? I've twisted the system inside out, right? I've taken the origin where the defect is, and that now becomes the boundary of ADS. I've literally turned the whole system inside out. And so I no longer see any conical singularity anymore. In the new vial frame, all that happens is that the ADS3 and the S1 might have different radii. But this here is a space, completely smooth, fine. You maybe worry about the fact that ADS3 has its own boundary. We'll brush that under the rug for now, right? In fact, life is even easier. The conformal anomaly vanishes. The geometric conformal anomaly vanishes on ADS3 cross S1, so I don't even have to keep track of the R squared shift, right? In this frame, since theta is just a circle, A being mu d theta is just some non-trivial monodromy on this circle. And so when you do your holographic calculation, all you're doing is you're assuming I have some ADS3 cross S1 foliated 5-dimensional geometry, and I play my holographic game. You can see this vial transformation very cleanly in the vacuum, where all it is a change between Cartesian and polar coordinates. I'm not going to waste too much time on this. So, to at least the people in the audience who understands what this means, let's specifically say what the problem is, right? We are looking for 5-dimensional solutions to something that will be some fermion variations that is of the form of some warp factor in front of an ADS3, some warp factor in front of a circle, and then I have to have a radial coordinate because I want this to be a solution in 5-dimensional gauge supergravity. And then my gauge fields also can depend on my holographic radial coordinate, but they only point along the circle. All right? There's also some scalar fields that come along for the ride, but they're not doing anything interesting. Once I've picked this ADS3 cross S1 foliation, I can ask, well, what's happening with this S1? When I did my switch from Cartesian to polar coordinates, I have to make sure that this circle, as it degenerates smoothly everywhere. That just gives me some regularity in the bulk. That gives me the boundary conditions at the interior of the space, right? That's important. You need to impose that. But again, I want to emphasize, asymptotically, this ADS3 and this S1 can have different radii. And there's a different vial frame where I am in flat space with a conical singularity. But in this vial frame, there is no conical singularity on the boundary, and I definitely do not want there to be a conical singularity in the bulk, or I can't actually trust my weak curvature supergravity approximation. So that gives us these boundary conditions that happen in the interior. And then, it's in fact buried here. So I take my 5-dimensional solution, and I look at it as I go towards the conformal boundary, and I see that this warp factor will blow up with some radius of the ADS3. This warp factor will blow up with the radius of the S1. And if n is not equal to 1, these radii are different. There's in fact an exact matching. The ratio of these two guys is literally n. I forget what, yeah. But it's exactly in there. So that would be boundary conditions that you impose in the UV. And this is the usual game in holography, right? I say what the sources are, that's boundary conditions on the conformal boundary. And then I say, well, I want my solution to be regular, and that gives me some regularity conditions in the interior. That's the holographic system that we're studying.
Sorry.
Yeah.
In the UV, you only have the ADS5 or something like that.
Very good question. So, everywhere away from the defect, if I assume that I have these asymptotics, this ADS3 is blowing up in the right way, and the S1 is blowing up in the right way, that everywhere here it is asymptotically locally ADS5. That's not actually true on the defect. It's if I get to the open questions, that's a big open question. But indeed, everywhere away from the defect, there is a UV that is locally asymptotically ADS5. You can pick the file frame where it is ADS3 cross S1 sliced.
But then, away from the boundary, this is no longer true, or is it?
Oh, away from the boundary, some other matter fields get turned on, the curvature changes, and it's just some 5-dimensional manifold with this reasonably simple warped product structure.
But you don't interpret it as a natural flow.
This isn't an RG flow, there's no scales.
Yeah, exactly.
Yeah.
But yet it's not
No, I mean, I can talk about being far away from the defect in the sense of taking a factorization limit in an OPE. But yes, there's no scales, there's no RG flow here. There's just a solution that has a boundary and a regular interior. That's maybe not obvious because when I tell you that there's an ADS3 and an S1, those have scales in them. But you could do a Weil transformation to get rid of them. Okay, so that's the framework. I haven't even told you what the theory is, but there's a reason the paper is 90 pages, right? Yeah. I mean, that's a good question, right? So the boundary conditions in the interior are that this circle, the theta circle degenerates in such a way, that's this fact here, h squared over f squared. If it vanishes quadratically with coefficient 1 in front of it, then y and theta locally at the core are just regular non-singular polar coordinates because I've always fixed theta to be period 2 pi. That's the boundary condition in the interior that you have to keep track of as you're doing all of this. And it's secretly built into all of this. But it's crucial that you impose that. Otherwise, you have some codimension 2 conical singularity in your supergravity, and I certainly don't know when, if I'm ever allowed to trust that.
So, sorry.
Yeah.
That condition you're putting it for every set of the one that's
The parameters.
y minus y0 to square.
That's just the boundary condition in the interior. It geometrically is the statement that, right, so here is in my usual coordinates, so I have the radial distance away from the defect and some flat slicing radial distance. I switch to coordinates. Along each one of these rays is an ADS3, and this angular coordinate is what I've called y here, right? So I'm just assuming that this is a good axis of symmetry with no conical singularity. That just boils down to some sensible boundary conditions in the interior for these metric functions. And there are the gauge fields and the scalars. They also have to be smooth. There's a killing spinner. It also has to be regular. You make sure everything is regular there. It's not a singular point. That's the point.
But I can imagine that there is something extending the value.
I mean, if you work in cylindrical coordinates, when you do Poincare ADS, you could take the origin and follow it to the boundary, right? But it's not a singular point. It is, of course, a preferred point because it's the fixed point of rotational symmetry. That's an important point, but it's not. It's a totally smooth point in space. Yeah. So the actual system that we're going to study, there's 2 of them. The obvious one, the first one that everyone learns when they do holography, is we're going to study the holographic dual of n equals 4 super Yang-Mills. which means that we're going to look at ADS3 cross S1 foliated solutions of 5-dimensional gauge supergravity with some non-trivial monogamy around the S1. As I tried to argue previously, and you'll just believe me, even though this original theory is n equals 4, if I turn on a bunch of non-trivial monogamies, I will generically break things down to 0,2 SUSY. Right? The global symmetry is SU4R, and there is a U1R symmetry and 2 flavor U1s with respect to the 0,2 symmetry. So there will be 3 μ's that I can turn on in that system.
So is that because you pick up one of the URLs?
Yes, I'm saying this is, you have all 4 killing spinor equations, and I'm saying I'm solving the 4th one. That's why it breaks this way, yeah. You could, of course, talk about asking the same problem for a less supersymmetric theory. There's a lovely example that we use a lot in holography, the n equals 1 Lee Strasser fixed point. That is a theory with the U1R and SU2 flavor symmetry, and so the maximal torus is 2 U1s. There's 1 flavor and 1 U1R. You can think of this n equals 1 Lee Strasser theory as decomposing your n equals 4 theory in n equals 1 language. In n equals 1 language, there is 1 vector and 3 chirals, and you flow to the n equals 1 theory by turning on a mass for one of the 3 chiral multiplets. Now, because that theory only has n equals 1 supersymmetry, the coupling runs, and this will, even if your original n equals 4 theory was weakly coupled, you will always run to a strongly coupled fixed point. So, n equals 4, I can try to make comparisons to free results. This Lee Strasser theory, there's no weak regime of it. It's just an intrinsically strongly coupled theory. And indeed, let's remind ourselves of the counting. N equals 4. There will be 3 monogamy parameters. In the n equals 1, there will be 2. Now, the U1R monogamy is always going to be linearly related to the conical deficit or excess. So I have a conical singularity and 2 parameters, or a conical singularity and 1 parameter. If I then take my defect in n equals 4, and I want to turn on that chiral mass term to drive the flow, I have to ask, is turning on that mass deformation compatible with the monogamy defect? It's a not that difficult exercise, and the answer is, it's not always. You look at some background chiral multiplet, that's the mass term, and this variation tells you that your mass that you want to be constant, the supersymmetry tells you, well, it actually needs to be covariantly holomorphic. For it to be covariantly holomorphic, that's also constant if A1 plus A2 minus A3 is 0, which means that this particular linear combination of these 3 U1 monogamies is 0. So, I have the n equals 4 monogamy with 3 parameters. If I fix them in some particular way, I can then turn on a mass and flow to the n equals 1 theory. If I do that, I can then make comparisons. As we said, you have to dial n to be able to integrate b. These are the equations that you're solving. But again, from a holographic perspective, and in that conical deficit is easy. It's just changing the ratio of the radii of your ADS3 versus your S1. Right? Let's get this in a little bit more detail, just so I will familiarize you with the labels that I'm using, so that when I write an expression, it's not completely devoid of meaning. Right? So, the supersymmetry constraint, this is telling you precisely which of the spinors we've picked out. This particular linear combination of the fluxes or monogamy parameters, whatever you want to call them, the mu's, this has to be related to the conical deficit or excess n by this relation here, where this plus or minus is the choice of whether I want chiral or antichiral symmetry, whether it's 0, 2, or 2, 0. For the rest of the talk, I'm just going to fix this to a plus, so it's 0, 2. We keep all the signs hopefully correctly in the paper, but it's easier to present it with a fixed choice here. When I show you what the answers are, I'm going to write them both as a function of these 3 mu's and n's. Remember that implicitly, this relationship is always assumed to be enforced. These are always really only functions of 3 variables.
So
Yep.
is the statement that for generic mu's you have 2, 0, 0, 2, and you can have enhancement, or you cannot just produce something that's more supersymmetric?
I think I think there are some special points of enhancement. Yeah, there's a 2-2 enhancement point. Yeah, I'm not going to, maybe it'll show up in a diagram and we'll see where it is, but I think there's a 2-2 enhancement point for the n equals 4 theory. Great. Let me just say in words how we do this calculation, because it's brutal, right? You're doing holography, you have to solve either second order equations of motion, or if you're looking for supersymmetric solutions, you're looking to solve first order BPS equations. These are hard, nonlinear, in our case at least ODEs, but nonlinear ODEs. Maybe you throw them on a computer, but that's not very enlightening. You don't get to extract that much analytic data. However, sometimes supersymmetry is magical. Sometimes when you look at your BPS equations, you see that you can construct constants of motion built out of the various fields and spinor bilinears. These are not constants of motion for any on-shell solution. They're only constants of motion for BPS solutions. This is related to equivariant localization. If you ask me about this at the end, I could say a few more words about it. Roughly speaking, what happens? This BPS equation of motion is constant over the whole solution. If I expand it near the boundary, it just tells me the one-point functions of the currents, for instance. And if I expand it near the core, it's some non-trivial function of all of the dilatons in the system. But this is supersymmetry. There's an attractor mechanism that fixes the values of those dilatons at the core of the defect to being related in some non-trivial way to the asymptotic charges, which in our language means it is some non-trivial function of J and mu. So looking at these gives me some non-trivial relation that will fix J as a function of mu if I can solve it. And then you have to do a lot of work to solve it. What that means is that when you look at the BPS equations and you identify E in this way and you work out carefully how the attractor mechanism fixes things at the core of the defect, you can extract and find the one-point functions for all of your fields without actually solving the BPS equations. If a solution exists, you know what the answer is. Now, if you're a good student, you still do the homework of making sure the solution exists, but that's amazing, right? I mean, you just pulled the answer out without actually doing any calculation. It's wonderful. This is the sense in which it really is just a piece of the story of equivariant localization. You have to make sure it exists, though. But I'm just gonna, this is the story of how you magically extract these solutions without, how you extract one-point functions without actually solving the BPS equations. And then what we did is we just numerically solved them to confirm that they exist in the parameter spaces that we expected. So let me just tell you the answer.
Sorry.
Yeah.
You don't have examples of analytic solutions.
In the n equals 4 case, we do. It's a double wave rotated black hole. In the n equals 1 case, no, I don't know. There's a hypermultiplet in that case, and it's messier. Yeah. We can discuss more later. It's an interesting point. So for the n equals 4 defects, you have your 3 U1s. You have 3 current one-point functions. There are these very clean, rational functions of mu. Remember that n is related to the sum of the mu's. And the stress tensor, well, supersymmetry relates it to the expectation value of the R symmetry because they're in the same multiplet. So I know HD and I know the J's. You look at this and we said mu's all live on circles. These functions are clearly not periodic in mu. Secretly in the quantum field theory, there's boundary conditions that you impose that break this shift symmetry. So these are not immediately wrong because they don't respect the shift symmetry of the monotomies. These are the answers. This is the differential you have to integrate. This is just repackaging all of those PDEs that we had, where here, only new ingredient is A. A is the A coefficient of n equals 4, which at infinite n is just n squared over 4. So you take this differential, you plug in these expressions. First you check that dB is exact. That's non-trivial, but it is. And then you integrate it. And you get some cute closed form function. It's proportional to n squared times n times this function f minus 1, where f is just this product of mu's that vanish at various values. Right? That's it. This is the computation that we did. You can ask, does this agree with the free result? It's a good question. Some people in the audience worked out the free result. The free result is only done without a conical deficit, but free n equals 4 super Yang-Mills is a really easy theory, and you could do it. I will say for a few people in the audience, you have to be careful about what those boundary conditions for the singular modes are. That's these parameters, Xi and Xi bar for a boson and Xi for a fermion. You have to make some choice when I try to match. In my holographic calculation, I never said anything about what the boundary conditions for the microscopic fields are. I don't see that. That's just not something that you have access to. You, in theory, could extract it if you carefully calculated 2-point functions and worked out how those 2-point functions saw it from 2-point functions in the free theory, but we didn't do it. Instead, we looked at the results for what B is for a scalar and a fermion. It's these expressions with these values of Xi, and we figured out that there's a really simple rule. If your monodromy is positive, then Xi is 1, Xi bar is 0, and the fermion Xi is 0. If Xi is negative, I shift it by 1 to make it positive, and then I pick this other assignment. You make these choices, you plug that into these formulas, you get this result, which is exactly this result. The only difference, of course, is here. There's an n squared minus 1, but we're at infinite n. So we did a calculation for n equals 4, and maybe surprisingly, maybe unsurprisingly, it actually can be matched exactly to the free result. Yeah.
I mean, there is another marginal definition found that equals 4, which is another least classical definition, the beta definition.
Yeah.
If you studied that theory, you expect that this would be independent of beta.
It should be. I don't know. I haven't done it. It's a good question. I don't know how general the argument of beta being independent of bulk marginal couplings is for 0, 2. But I think it should hold in that case. Just for future fact, you can also calculate the on-shell action, and you see that the on-shell action gives you 12an minus b. We'll come back to this if I have time. First, you have to do your homework. You say, when do these solutions exist? These are plots. The dashed line is where the boundary would be if we could always use our mu to mu plus 1 shift symmetries. That would be a range of parameter space that ought to exist. You'll notice, though, that there's this solid blue line. The solid blue line is where the solutions actually stop existing. And so, for most of the parameter space, they happily exist. But there are these corners of parameter space where nothing goes wrong. Your monodromies all satisfy the signs that you expect them to. But the bulk dual seems to go away. It's not a smooth bulk dual, or we can't identify it. Maybe there's some symmetry breaking in that corner that we don't understand. This is a big open question. What exactly is happening in these corners? Okay, so I told you that you could do this calculation for the 0, 2 defects in n equals 4, and you can match them to free results. You do exactly the same thing for n equals 1. The only thing that's different is that because I have to be able to turn on the n equals 1 mass deformation, I have one constraint on my mu's. So now I only have 2 mu's. I have n, or the u1r, and I have 1 flavor mu left. You go through the calculation, you get expectation values for currents. You look at the differential, and you integrate it. Functionally, it's very similar, right? It's basically the a coefficient times some function minus 1. And this is 1 minus mu over n, but these numbers changed. Only things, this overall function that's related to a, this number changed, and I have a 4/3, 4/3, 2/3, whereas previously those were all 1s. That's the only difference. Similarly, you calculate the on-shell action, and it similarly looks like 12an minus s, where this is now the a of the Lee Strasser fixed point. Great. I have b for n equals 4. I have b for Lee Strasser. Is there a monotonicity? I have turned on a bulk RG flow, not a defect RG flow, and no, there isn't. B increases, right? If I don't have a conical deficit, it's easy. All of this stuff in front vanishes. This is 4 times 2. This is 4 times 3. So you get a factor of 3/2. B alone is not monotonic under bulk RG flows. You could never see this from free results because, of course, the free result is just counting degrees of freedom. Here we see it increases. Indeed, if I allow myself to include the conical deficit, it can increase or decrease. That's fine. That's a plot of it. If you look at the on-shell action, which is this 12AN minus B, the expression for it is ugly. I'm not going to put it on the slide, but it was there and it's for sure in the paper. It turns out you can explicitly show that S, the on-shell action, always decreases with or without a conical deficit or conical excess. To me at least, this is strongly indicative that 12AN minus B, or in the flat case, 12A minus B, should be another RG monotone for bulk RG flows. Now, in our example, in the flat case, B increased, but it doesn't have to decrease. It doesn't have to increase. It can decrease. If this is a monotone, delta A bounds how much B could possibly decrease, but it could increase as much as we want. This is our conjecture, that this is a monotone. Now, we have a data point of 2, the general free theories where it's easily true, and this one example. But that's more than 0. And it's hard to do these calculations of strong coupling. But I'm going to, why did I think I could do this? You can ask me about the 3D 1D case. What did we do? We studied 0,2 magnetic defects. We showed that the n equals 4 system can be matched directly to the free results. And we showed that if you consider flowing to the n equals 1 Lee Strasser fixed point, B can increase or decrease, but this new combination, 12AN minus B, appears to be a good monotone for bulk RG flows with defects. It doesn't quite work as nicely in 3D. That's what we skipped. And I was told to put open questions up, but I think I'm out of time, so I will stop here and you can read these. Thank you.
I have a question.
Yeah.
So in this new quantity, this 12A minus B.
Yeah.
So if I don't flow in the bulk, so I just have a defect RG flow, then you have minus B, no?
Yes, so then it will increase. Yeah.
It will increase.
Yeah.
So, I mean, because in my mind I would like to have a nice quantity that works in both limits, only bulk and only defect RG flow, no?
I mean, we want lots of things in this world, right?
No, I understand.
I mean, if in this example B had also decreased, I would have been happy. Our lives would be much easier. But feel free. I mean, someone peer-reviewed the papers, but if we made a mistake, I would love to know it. If it turns out that B really actually is decreasing and we screwed up, it would make all of this much cleaner and easier.
No, I know B
But-
doesn't decrease, that's established.
Yeah. But, yeah. So, the lesson seems to be that purely defect RG flows and bulk RG flows just have to be treated differently. I agree, this is disappointing, because you could imagine turning on both at the same time and seeing what happens. That's related to one of the open questions here, which is, it would be lovely to do that. The problem is that when you're doing holographic renormalization of these systems, almost all of the boundary is locally asymptotically ADS5, so we know how to do holographic renormalization, and we know how to turn on sources, read off all of this data. Exactly the defect. That's the part of the boundary that's the boundary of the ADS3 slice. And it's not locally asymptotically ADS3. And it is just not known, in general, with holographic defects. It is not known, except in very specific cases, how to do holographic renormalization to understand defect operators in holographic systems. I think that's why it's the last one. I think that's one of the biggest questions in this framework of holographic defect theories.
Go first. So, can you say again where did you get this 12A and minus B?
Sure. I mean, you could just pick up anything and come up with it. 12AN minus B is what falls out when you calculate the on-shell action.
The supergravity on-shell action.
Yes, the free energy of the defect. Now, there's some non-trivial renormalization. There's a volume of ADS3 that you can do something that smells like zeta function regularization and turn this into like a minus 2 pi. But
So
this is the bulk on-shell action, which should be related to the free energy of the system.
So that means that if I compute this thing for any other supergravity solution corresponding to other defects, I don't know, Gukov-Witten defects, I should get the same thing.
I think so, we haven't shown it.
Okay.
But I mean, there probably is precisely an argument that uses exactly the anomaly polynomial and tells you indeed that 12an minus e for a conical codimension 2 defect in 4 dimensions should look like this.
Yeah, I think you can do that. If you take CFT as 4 with S2 defect,
Yeah,
you get this on the node.
okay, yeah.
I know for without conical defect you get 12a minus b. That's
Yeah.
easy. I believe, yeah,
I don't, yeah, so I certainly, when you play all of those games,
from the anomaly, from the
Anomaly
special
will
test
not.
test.
yeah, it's just integrating the anomaly.
Okay, right.
When n equals 1, when n is not equal to 1, it probably, but I don't know.
I think it works.
Okay.
Yeah, but okay. There's this comment that we had already in private,
Yeah.
but maybe I can make this. This seems to be very specific to 2D for these systems, right?
Yes.
Because when you do it for odd dimension or defects.
Indeed. So I will just say the punchline of the 3D 1D story. So the 3D 1D story looks similar. There's a G function because it's a one-dimensional defect. The G function increases. You can then say, let me calculate the free energy, and the free energy for n less than 4, the free energy always decreases. For n greater than 4, it can go either way. So just looking at the free energy clearly isn't the full answer because 3D 1D it doesn't work. Again, modulo is having made a mistake. Yeah.
We expect this quantity 12a minus b to be sensitive to bulk marginal couplings.
Well, this is the question, right? A shouldn't be. So there are arguments that with some amount of supersymmetry, I think, B can be independent of bulk marginal couplings.
Well, if the I think it's the marginal coupling generates some SUSY preserving.
Yeah. Thank you. That's why I don't. You can explain. So with some supersymmetry, yes, it could. So indeed, if you had a system where I had you'd have to break supersymmetry, and so I don't know how you would easily do the calculation, or maybe you could do it with less supersymmetry. Yeah.
So, in view of the time, I suggest we ask any remaining questions over coffee, and let's thank Matt again.
Thanks.